Hello, everybody. This is our second and last lecture dedicated to the elements of crystallography. In this lecture, I will introduce a language used in crystallography to indicate directions and planes in a crystal lattice. I will say a few words about the arrangement of atoms in crystallographic planes, that is Bravais lattices in 2 dimensions. And then I will tell you what is so special about cubic lattices as compared to other Bravais systems. So let's go. To indicate the notation to indicate directions in a crystal has been invented not by William Miller, an English crystallographer. I learned just 10 minutes ago that actually it has been invented about 20 years before Miller by a German crystallographer, Christian Weiss. Anyway, so the idea is William Miller published not as his own, it was not plagiarism, but he probably popularized and maybe improved somehow this notation. So anyway, this invention has several fathers. A direction in crystal can be specified by a direction vector, d, and this vector may have unit length. When it comes to crystals, just saying that, so here is my direction vector with the components 1, 0, 0, this doesn't convey any information unless you indicate how your Cartesian coordinates are aligned with the crystallographic axis, with these translation vectors A, B, C, about which we spoke in the previous lecture. So instead of using arbitrary coordinate system, we express this direction vector in terms of the translation vectors. And so the direction vector is a linear combination of the translation vectors A, B, and C with integer coefficients I, J, and K, like here. So this notation, this expression for the direction vector tells you how many steps you need to make in each along each translation vector to get from the beginning of this direction vector to the end of the direction vector. So these integer coefficients I, J, and K, they should not have a common factor. I mean, they may have a common factor, for example, 1, 1, 2, and 2, 2, 4, but if they do, that means that it is the same direction. So conventionally, these integer coefficients are placed into square brackets for directions, and if one of these components, I, J, K, turns out to be negative, then the minus sign is placed not in front of a number, let's say -1, but on top of a number. So it would be 1 bar or over bar. All right, so here are some examples. A triclinic lattice, so arbitrary translation vectors, arbitrary angles between the translation vectors. So these are the simple directions. So this is, for example, this one, 1, 0, 0. So this is the translation vector A. You make one step in the direction of the translation vector A and do not move in the direction of the translation vector B and translation vector C. This one here is -1, 1, 1. So -1 step in the against the translation vector A and +1 step along the B vector and +1 step along the C vector. Let's say this is B and this is C. All right. Now, in some situations you may have in some crystal systems, you may have a whole family of such direction vectors which are related to each other by one of the point symmetry operations, like typically a rotation. So if you have a family of such symmetry-related directions, then they are indicated with the Miller indices of one member of that family, and it is placed in triangular brackets. Yeah. All right. Now with planes, let's move on to planes. It's a little bit trickier. So the natural way to indicate the direction of a plane is to look at the vector which is perpendicular to that plane, indicate the Miller indices of that vector, and assign those Miller indices to the plane to which the direction vector is perpendicular, right? People do not do that. They use a different convention and a different method to uniquely determine the Miller indices of a plane, and it is based on the intercept method. So the intercept method is slightly more complicated than what I just said, what I just described. So let's say you have a plane and it intersects the crystallographic axis built on the translation vectors. Translation vectors are not necessarily perpendicular to each other, so this is not necessarily a Cartesian, orthogonal Cartesian system. So you look at the intersection points of a particular plane with this crystallographic axis. And somewhere you have the origin. Now, it may turn out that the plane goes through the origin, in which case you simply switch to another plane which is parallel to the original one. So this intersection point should not be zero. And then you express the intersection points with the coordinate axis, which are aligned with the translation vectors, in terms of the lengths of your translation vectors. So let's say those intersections are at PA, QB, and SC, where P, Q, and S are some numbers. You invert those numbers, 1 over P, 1 over Q, and 1 over S. Then you multiply each member of this triplet, 1 over P, 1 over Q, 1 over S, with the smallest integer, n, that turns the numbers n over P, n over Q, and n over S into integers, and those integers should not have a common factor. Because again, if they do have a common factor, then it is perfectly legit, but so a plane with Miller indices 1, 1, 1, and a plane with Miller indices 2, 2, 2 is one and the same plane. So this triplet of integers, n over P, n over Q, and n over S, are the Miller indices of the plane, and they are placed in the round brackets. So open round brackets, ijk, close round brackets. And again, if it turns out that one of those numbers, or several, or 2 or 3 of those numbers turn out to be negative, then you place the negative sign not in front of the number, but as an overbar above that number. Now, the reason why this slightly more complicated method than the one based on specifying the Miller indices of a perpendicular vector, direction vector, why this more complicated intercept-based method is used is because of it is more convenient in experimental measurements of the determination of the crystalline structure based on the X-ray diffraction methodology. In the X-ray diffraction methodology, they measure the so-called reciprocal lattice, and the reciprocal lattice vectors are have Miller indices which correspond to the Miller indices of the direct lattice planes to which they are perpendicular. And the direct lattice Miller indices must be determined using this intercept method. So that's the reason, but I know you probably, if you are not familiar with the topic, you can look it up. If not, you can either look it up or forget about it. All right, anyway, let's keep moving. Here are some things that I have already said. So yes, if one of the Miller indices turns out to be 0, that means that a plane is parallel to a particular coordinate axis. So this is the coordinate axis, this is the plane, they are parallel to each other. That means that they intersect at infinity, and 1 divided by infinity is 0. Now, a family of symmetry-related planes which have not the same Miller indices, but so you can transform from one plane to the other to another within that family by applying the point symmetry operations of the crystal. So a family of these symmetry-related planes is indicated by taking the Miller indices of one member of that family and placing them in curly brackets. So here is an example of the symmetry-related Miller indices planes with the Miller indices 1, 0, 0 in a cubic lattice. So 1, 0, 0, 0, 1, 0, 0, 0, 1, negative 1, 0, 0, 0, negative 1, 0, 0, 0, negative 1. All right, so here are some examples of planes with given Miller indices. So for example, this one has Miller indices 0, 0, 1. So this is the x-axis. This is a cubic crystal, unit cell of a cubic crystal. Here is the x-axis pointing out of plane of the figure. Y-axis points to the right, and z-axis points up. So this shaded plane does not intersect the x and y axis. So the intersection points are located at infinity, and this plane intersects the z-axis at the position 1 lattice constant. Now we have the intersection points at infinity, infinity, 1. Invert them, you get 0, 0, 1. And likewise for these two. Here, this shaded plane intersects the x-axis and the z-axis at 1 lattice constant and is parallel to the y-axis. So the intersection points are 1 for x, infinity for y, and 1 for z. Invert these numbers, you get 1, 0, 1. And similar for these ones. And finally, this example has the intersection, the plane here. Well, this is the part of the plane, portion of the plane. It intersects the x, y, and z axis at 1 lattice constant. So 1 over 1 is 1. So the Miller indices are 1, 1, 1. Okay. In a crystallographic plane, the lattice points are arranged periodically. They have translation symmetry. They form Bravais lattice, but that Bravais lattice is a two-dimensional Bravais lattice. So a natural question arises, how many two-dimensional Bravais lattices are there? We already know that in 3 dimensions, there are 14 Bravais lattices. In 2 dimensions, the situation is even simpler. There are only 5 distinct Bravais lattices. Here they are. So the least symmetric one. So the philosophy of Bravais lattices in 2 dimensions is the same as in 3 dimensions. So a Bravais lattice is a collection of lattice points in a plane. You can reach any lattice point from any other lattice point by making an integer number of steps along the 2 translation vectors, which I call A and B. The angle between the 2 translation vectors can be either arbitrary, or it can have special values, which are either 90 degrees, or 120 degrees, or 60 degrees. If there is no special relation between the angles, between the lengths of the translation vectors, they are not the same. They do not differ by like a factor of 2 or anything, right? No relation between them. And the angle between the translation vectors is arbitrary, then we get the least symmetric Bravais lattice in 2 dimensions, the oblique lattice. If the 2 translation vectors are the same in length and the angle between them is either 60 degrees or 180 degrees, then this gives us, not 180, 120 degrees, then this gives us the hexagonal lattice. And the primitive cell of a hexagonal lattice is a rhombus with the angles 60 degrees on 2 opposite angles are 60 degrees and 2 other angles are 120 degrees. Then you can have, and I mean, the reason why it is called hexagonal is obvious because this figure is a hexagon. Then we have square lattice, is probably the most, yeah, not probably, it is the most symmetric one of all. The angle between the 2 translation vectors is 90 degrees, and the length of the vectors A and B are the same. And finally, we have rectangular Bravais lattice, different lengths of the translation vectors, but the angle between them is 90 degrees. Rectangular lattice is actually a family of 2 members: the primitive rectangular or simple rectangular lattice and the centered rectangular lattice, which is obtained by placing an extra lattice point in the center of each of these rectangles. Now, it may look like, it may immediately seem that there is no fundamental difference between the rectangular centered lattice and the oblique lattice, right? Because there is no special relation between the translation vectors A and B, they are not equal. And the angle between the vectors A and B is arbitrary. But the reason why the rectangular centered lattice is a special type of lattice, is different from oblique lattices, is because it has reflection symmetry. So if you, for example, produce a reflection relative to, for example, this line, this vertical line, this horizontal line, sorry, or this vertical line, let's say around this vertical line, then this point goes here, this point goes into this point, they get swapped. Whereas such a reflection is impossible for oblique lattices. So rectangular centered lattice is more symmetric, has a higher degree of symmetry than oblique lattices. All right, now let me tell you about the special role of cubic crystals. Previously, I mentioned that in principle, you could indicate the plane Miller indices for plane by specifying the Miller indices for a vector perpendicular to the plane, for the direction vector. But instead, conventionally, everybody uses the intercept method. And for a general lattice and any non-cubic lattice, the Miller indices of a vector perpendicular to the plane and Miller indices of the plane itself are different. They are not the same. However, for cubic lattices, and only for cubic lattices, they are the same. And on this slide, I want to convince you why it is so. So let's say you have a cubic crystal. The translation vectors are aligned along the Cartesian axis, coordinate axis x, y, and z, which are perpendicular to each other. And let's say you have a plane with the Miller indices I, j, k. And this plane intersects by construction of the Miller indices for a plane. This plane intersects the coordinate axis at the positions which are inversely proportional to the Miller indices. So 1 over I, 1 over j, 1 over k. And the proportionality constants, now, of course, you measure the distances not in just numbers, but in lattice constants. So multiply this with lattice constant a, and multiply this with this integer n, the smallest integer, such that if you invert the intersection points, then you will get a pair of integers, a triplet of integers. So following this recipe from here. No, from here. All right. Now, I ask myself a question. What is a vector perpendicular to this plane? How to construct a vector perpendicular to this plane? And the answer is this. I need to take two vectors that belong to this plane and are not parallel to each other, and they form a vector product of these two vectors. Now, if you form a vector product, so let's say this is your vector A and this is your vector B, and this is my right hand. I'm not sure if the picture is inverted or not, or mirror reflected or not, but this is my right hand. So A, B, and the vector product of vectors A and B by the right hand rule will be shown in its direction is the direction of my thumb, perpendicular to A and B. The vector product of two vectors is perpendicular to both vectors. Okay, so how do I? So all I need to do is to take two vectors, let's say R1 and R2, that belong to this plane. I choose my vector R1. It starts at the intersection point of this plane with the x-axis and ends at the intersection point with the y-axis, like this. The vector R2 starts at the intersection point with the x-axis and ends with the intersection point with the z-axis. And now to form the vector product, I recall that the well-known facts that a vector product of unit vectors in the x and y direction is a unit vector in the z direction. Then the vector product obeys this cyclic permutation rule. So if my y go in the first formula, my y goes to the first place, my z goes to the second place, then my x would go to the third place, a cyclic permutation, like this. And also, if the terms in the vector product are swapped, then the result changes sign. Okay. A cross b is the same as negative b cross 8. So using these rules, it is easy to form the vector product of these two vectors, R1 and R2, that belong to the ijk plane. And this is what I get. And I notice that so the unit vector in the x direction is divided by the product of the Miller indices, plane Miller indices jk. The unit vector in the z direction is divided by ij, the Miller indices. Notice that, for example, the x unit vector is divided by jk. J belongs to the y, k belongs to the z. The z unit vector is divided by ij. I belongs to the x, j belongs to the y. And the y unit vector is divided by ik. Now, I take the product ijk out of the brackets. And in the brackets, I get I x unit vector plus j y unit vector plus k z unit vector. But this combination I x unit vector plus j y unit vector plus k z unit vector is nothing else but a vector with the Miller indices ijk, the direction vector with the Miller indices ijk, the same as the Miller indices for the plane. Now, like I said, this doesn't work for any other crystalline system, but cubic lattice. So in cubic crystals, the planes with the Miller indices ijk are perpendicular to the vectors with the same Miller indices ijk, and vice versa. Another interesting property of this of the cubic family of crystals is that the distance between two adjacent parallel planes with the same Miller indices is given by this formula, the lattice constant divided by the square root of the sum of squares of the Miller indices, ijk. And here is the proof of this result. So in the previous slide, we have seen that a vector perpendicular to the plane with the Miller indices ijk has the same Miller indices. So ix plus jy plus kz. Now let us turn this vector into a unit vector. To do that, we divide this vector by its length, which is the sum of squares, which is the square root of the sum of squares of the x, y, and z components of the vector. Those components are the indices ijk. Now, so we have a unit vector perpendicular to the plane with Miller indices ijk. Now, let us look at the next adjacent plane with the same Miller indices, and its intersection with the coordinate axis x, y, and z is the same, but the integer n needs to be replaced with n plus 1, because it is the n plus first plane so the intersection points of this next plane would be n plus 1, a over I, n plus 1, a over j, and n plus 1, a over k. Now we can draw a vector that starts on the nth plane and ends on the n plus first plane. So for example, we can take this vector to be along the x-axis. We do not have to. We can start on the x-axis and end on the y-axis. So the result will start on the y-axis, na over jy, and end on the z-axis with the coordinate. So na over g over j, y would be the beginning of this vector. The end of this vector could be n plus 1, a over k, and on the z-axis, and end on the z-axis. The result will be the same. So the simplest choice, start here on the x-axis and here n plus 1, a over I on the x-axis as well. So here is this vector. Now, the distance between two planes will be simply the projection of the vector d that starts on the plane n and ends on the plane n plus 1 onto the unit vector h hat, which is perpendicular to both planes. A projection of a vector onto a unit vector is simply a dot product of the given vector d and the unit vector h hat. And once you take the dot product, keeping in mind that the dot product of x with x unit vector with x unit vector is 1, x unit vector with y unit vector is 0, x unit vector with z unit vector is 0, and things like that. You end up with this result that the distance between the planes is the lattice constant divided by the square root of I squared plus j squared plus k squared, which is the length of this vector h vector. Again, I would like to emphasize again that this formula works only for cubic crystals. It doesn't work for all other types, Bravais lattice types. Well, thank you all for your kind attention. We are done with crystallography. I'll see you, I hope, tomorrow. Goodbye.